Привет! Today we will be looking at the proof of the second partial derivatives test. The previous video introduced this test and showed how we could actually use it in practice, but left the question of where this messy thing comes from for another day. That day has arrived. This thing takes up so much space that I'm going to get rid of it. Luckily, we won't need to refer to it because we will be deriving all this stuff from scratch. That's better. Suppose that p is a critical point of our function of two variables. We're just setting the stage here. Since f is a function of two variables, p, of course, is a point in R2. And remember, to say that it is a critical point merely means that the gradient of f evaluated at p is the zero vector. In the last video, we discussed why that is a necessary condition to have a local extremum at p. It's not sufficient. Not every critical point corresponds to an actual local max or local min, but this is necessary. This was the first in our two major steps in looking for local extrema. Finding the critical points narrowed down our list of suspects, and then we had to scrutinize each suspect with that gory second derivatives test that we will now be deriving. Anyway, let's draw a picture of what's going on. This is a function of two variables, so we can graph such a thing. I have my point P in the domain in R2, and the function f maps it to some point, maybe this one. Now we're looking for a condition that will tell us whether we have a local maximum here, or a local minimum here, or for that matter, a saddle point here, or in some cases, of course, we know we will just get an inconclusive test, but we would like to be able to point to something that will enable us to say, aha, it's a local minimum, or aha, it's a local maximum. And recall that in the calculus 1 case, that was easy, because if I had a critical point at p where the derivative was equal to 0, if I knew the sign of the second derivative of the function at that point, that could do the job. For example, if I knew that the second derivative was positive there, that means that the function was concave up there, and that tells me immediately that I have a local minimum. Similarly, if the second derivative were negative at p, then I would know that the function was concave down at that point, which would mean that I definitely would have a local maximum right there. And if the second derivative were 0, well, we couldn't say anything. Let's try to generalize that thinking up to this case. We might guess that some condition on the second partial derivatives would do the job. I know the first partials are both 0, that's what makes the gradient 0, but the second derivatives should tell me something about concavity, at least in particular slices of the graph. For example, if the second partial with respect to x is positive, that would tell me that if I looked at a slice of the graph like that, then inside that slice, the cross-section would be concave up like that, which makes this feel like maybe it's a local minimum. It's definitely not a local maximum if we have something like that. The problem is it could be a local minimum that way, but if I slice the other way, maybe it's a local maximum, and so that I actually end up having something like this, like a saddle point. But suppose that if I look at the second partial with respect to y, so I'm looking at the cross-section of the graph in that plane. Suppose that my second partial with respect to y is also positive, so that it is also concave up right there. Would that be enough to tell me that I've got a local minimum right there for my function? I'd have something that looked like this, which is certainly consistent with the idea that it might be a local minimum, but there's no guarantee. Remember, for it to be a true local minimum, it would have to mean that there is some neighborhood of that point p with the property that the value of f at p is less than the value of f at every other point inside that neighborhood. Now, just because I have a little skeleton like this doesn't mean that the whole graph, when I put all the flesh on it, is going to look like that. In other words, all may be well when I'm moving parallel to the x-axis or parallel to the y-axis, but it could still be the case that if I move in some other direction, if I am taking, say, a directional derivative in this direction, that I do not have a minimum in that direction. Maybe I have a maximum in that direction, in which case my point P would not be a local minimum of the function of two variables. I would have a saddle point there. Or I might have something even stranger. It might be that it goes down on this side and then up on that side like that. So I might have this one little spot right here where it's going down. I don't know. Just knowing what happens in two directions does not guarantee anything about what happens in all of the infinitely many directions in which I could move from point P. This is what makes functions of two variables trickier than functions of one variable. When you have only one variable, there's not a lot of choice in how you move from P. You can go to the right, you can go to the left, that's it. When you've got a function of two variables, there are infinitely many ways you can move from a given point. Okay, but suppose that somehow I was able to determine that the second derivative in every direction, in all of those infinitely many directions, if I was able to determine that the second directional derivative in every direction coming from P was always positive, that would tell me that I would have, if I look at any slice of the graph of f like this, I would always have a minimum there. And if that were the case, then yes, I could conclude that what I have is definitely a local minimum of the function. So that is what I want. That's what I need to somehow establish if I want to come up with a second partial derivative test. I'm going to need to know not only that P is a critical point, and not only that the second partials with respect to x and y at that point are both positive to get a local minimum in this case, but I'm going to need to know that all of the second directional derivatives are positive. If I know that, then I am in business. So let me write some of this down. Our observation here, if all of the second directional derivatives of f at P are positive, then f will have a local minimum at P. And of course, by the same logic, if all of the second directional derivatives of f at P are negative, then f is going to have a local maximum at P. In this case, we would be saying that all of those slices would give us cross-sections that were concave down at that point, which is why we would have a local maximum. This point represents the top of each one of those little hills in each direction. And so we really would have a little cap like this. There's a third observation we can make. If some of the second directional derivatives are positive at P and others are negative, then we're going to end up with a picture something like this, or some variation of it, where we have local minima in some directions and local maxima when we restrict ourselves to slices in other directions. That means we're going to have some kind of a saddle point. Then f has a saddle point at P. Incidentally, there can be kind of funny shaped saddles. Could be an ordinary saddle where you have places to put your legs and then it rises up in front and back, or you could have what's sometimes called a monkey saddle where there are 3 places going down, one for each leg and one for your tail, if you're a monkey, that is. And of course, it would go up elsewhere. You could have all sorts of strange things like an octopus saddle too. Doesn't matter. I'm calling them all saddle points when the function goes up in some directions and goes down in others. Okay, well, this observation of ours is very useful, because it gives us something that we can try to translate into analytic language. It offers some challenges, though. 2 of them, in fact. The first challenge is relatively minor, and that has to do with this notion of a second directional derivative. We've never computed such a thing, except the very special case of second partial derivatives. How do we compute a second directional derivative? In particular, can I come up with a formula for the second directional derivative in general, given a function and a direction? That's the relatively easy challenge. The harder challenge has to do with this universal qualifier right here, all. We're not just interested in computing a second directional derivative. We have to be able to conclude something about all of the second directional derivatives of a function at a point. There are infinitely many of them. How are we going to meet this challenge of being able to say something about infinitely many things at once? That's the harder part of the problem. Anyway, we're going to have to meet both of those challenges in order to make use of this observation and to turn it into an actual derivation of our second partial derivative test, which I showed you last time. All right, let's get to work on the first challenge. Our problem is find a formula for the second directional derivative of a function of 2 variables, whose graph, of course, we can think of as a surface, at point P, and as P could be, of course, any point in the domain of the function, P is given by its coordinates in the xy plane. So find the second directional derivative of f at this point xy in the direction given by a unit vector u hat. And since u hat is a unit vector, its tail will be at P, and its tip will be on some circle of radius 1 surrounding P, like so. And let's give names to the components of this unit vector. Let's call them h and k. So I'll put that down here as well, right here. Okay, now we have stated our problem. All right, for the purposes of this derivation, let's imagine that we are fixing this direction, and all we're thinking about is we could move this point. So we could say, what's the second directional derivative in this direction at this point? Or what's the second directional derivative at some other point in that same direction? So we're going to, for the moment, think of h and k as fixed. We will let them vary later, and these as being our two variables, the point at which we are taking that second directional derivative. If we're going to come up with a formula for this thing, we'd better start with some notation for it. The first thing I'll put down in my solution will be that notation. My notation for the second directional derivative will start off looking just like our notation for the first directional derivative, except I'm going to put a 2 up here as a superscript. So I'm not squaring anything, that just represents the second directional derivative. Notice, by the way, how compact this notation is right here. That p, we remember, is actually standing in for x and y, our variables, and that u is standing in for h and k, which give the direction in which we are taking the second directional derivative. All right, anyway, if this is the notation, what does it mean? The second directional derivative is, of course, the directional derivative of the directional derivative. And for the most part, we can just follow our nose to the solution here, because we know how to compute directional derivatives. We learned that in an earlier video. This stuff on the inside is going to be the gradient of f evaluated at p dotted with the unit vector. And to take that dot product, we'll first need to write out the components of those vectors, which look like this. This, of course, is just the definition of the gradient, and h and k we already specified will be the components of our unit vector. Now, taking the dot product in the usual way, this becomes this expression right here. This is worth dwelling on for a moment. Remember, we are thinking of h and k as fixed for the moment, because we're just thinking about what would the directional derivative be like in that specific direction if we vary the point at which we're taking the directional derivative. P, on the other hand, is standing for x and y, so that's where our variables are. So, for example, this first term right here, f was a function of two variables. You take its partial with respect to x, and you get another function of two variables. And p is just standing in for x and y, so this thing itself is still a function of x and y, and we're just multiplying by a constant. Similarly, this piece is a function of x and y, and we're just multiplying by a constant. So all of this stuff in parentheses is just a function of x and y, which is a good thing because we're taking its directional derivative, so it had better be a function of those two variables. Okay, but how do we take the directional derivative of this function of x and y? Well, we do it in the usual way. Namely, we take the gradient of the function in question and dot it with the unit vector in the direction we're interested in. Well, to do this dot product, first I'm going to have to find this gradient. The first component of the gradient will be the derivative of this stuff with respect to x. Well, that's easy, because we can take derivatives term by term. H is a constant, so it just sits there, and so we're really just taking the derivative of this with respect to x. Of course, that is going to be the second partial with respect to x of f, and the h just sits there, as we said. And now moving on to the second term, its partial with respect to x is going to be this. Because when I take the partial with respect to x of the partial with respect to y, I get this, partial with respect to y and then with respect to x, and then the k just sits there because it's a constant. Well, that's just the first component of this gradient. For the second component, I have to take the partial of all this junk with respect to y, and when I do that, I will get this, as you can verify on your own. And of course, I still need to dot it with u, and u is hk. Now I have to actually take that dot product, which gives me this. I can actually clean this up quite a bit, though, because these two middle terms are actually equal to one another. They both involve hk, and they involve a mixed partial. And we know that those two mixed partials are equal to one another. So that means what I really have right here is just two copies of either one of them. I'll say two copies of f xy to keep it in alphabetical order. All right, we are done. That's as much as I can clean it up. What I have shown is that this second directional derivative of f at p in the direction of u can be computed in terms of the second order partial derivatives of f at p. I'd have to compute the pure second partials, evaluate them, and the mixed second partials, and then just stitch them together along with h and k, where h and k, we remember, are just the components of the unit vector in which we're taking that directional derivative. And this really isn't that bad at all. By the way, this is not something you should commit to memory. We'll be using it in this one proof and nowhere else. I'm going to do a little housekeeping here and get rid of most of this stuff and just keep the result of our labors. Okay, that's better. We'll need that for future reference. Let's take stock of where we are in our derivation of our second partial derivative test. We're supposing we have a critical point of our function of two variables, which means it's a suspect for being a local extremum. We have observed that it will be a local extremum if all of the second directional derivatives at that point have the same sign. If they're all positive, then we will have a local minimum. If they're all negative, then we will have a local maximum. And we have come up with a formula for the second directional derivative, which we'll now put to use. I'll draw a little flowchart down here to show the logic. We want to show that f has a local extremum at the critical point p. We've said that this will happen if the second directional derivative of f at p has the same sign for all choices of u. In other words, for every possible direction we could move from p. Next, I'm going to make an algebraic move that will look a little strange. You will be able to appreciate its significance, though, shortly. For now, I want you to just be able to verify that the logic involved is correct. We can discuss the strategy of why I'm making this move once the whole argument is done. Okay, here's the idea. If I take any number whatsoever and divide it by a positive number, I preserve the sign of the number that I started with. This is simply because if you divide a positive by a positive, you get a positive. And if you divide a negative by a positive, you get a negative. For that matter, if you divide 0 by a positive, you get 0. So dividing any number by a positive number preserves its sign. This is a fact we'll be able to use because we're not interested in the value of this second directional derivative. All we are interested in is its sign. So if we do something that changes the value but preserves the sign, that's fine as far as this derivation is concerned. And that's what I'm going to do right now. I'll note that this condition will be satisfied if, and only if, this condition is satisfied. Now these are identical, except I have taken the second directional derivative and divided it by k squared, which is of course a positive number. So whatever this is and whatever this is, they have different values, but they have the same sign. And all we care about is the sign here. So if these always have the same sign for every possibility of unit vector u, so will these, in which case we know we will have a local extremum. Very well, you can see the logical equivalence of these two statements, but why on earth would I be interested in something like this? The reason I'm interested in this funny expression right there has to do with this stuff right here. Our second directional derivative, which is given by all of that stuff, if I divide it by k squared, I get a very nice form. And this is not the sort of thing you would notice at first glance, but only after many hours and days of banging your head against this particular problem. Anyway, when we write out this expression right here, in other words, when we divide all of this stuff by k squared, what we end up with is this expression right here. And since this is just standing in for this, I can say that this stuff has the same sign for all u, if and only if this stuff has the same sign for all u. But u, let us remember, is the vector hk. So I'm going to go ahead and replace that u with h and k. Okay, but you may be wondering, why did I write h over k in blue here? Was this just to get a little more color in the bottom half of the screen? No, this was not done for aesthetic purposes. This was done to be suggestive. This shows that the expression I have right here can be thought of as a quadratic polynomial where the variable is h over k. I've got a squared term and a linear term and a constant term. This, after all, is just a constant. So I've got a constant times the square of the variable, a constant times the variable itself plus some constant at the end. Well, that should make us very happy because you have known all about these sorts of things back since you took your probably first or second algebra class many moons ago. In fact, you know something about the graphs of quadratics, that if I have the independent variable on the horizontal axis, so this would be my independent variable h over k, and the dependent variable on the vertical axis, so this would be the value of all of this stuff, which is this, so I'll make that our label on the vertical axis. Then the graph of this quadratic would be a parabola. Now, the precise details of the parabola are not things that we particularly care about. All we care about is whether the values on that parabola all have the same sign for every possible input. Now, to have the same sign, that would mean we would have something where either the entire parabola was above the horizontal axis, so that it's always positive, or the entire parabola was below the horizontal axis, so that it's always negative. What we don't want is something like this, where it actually crosses the horizontal axis, where sometimes it's positive and sometimes it's negative. So we ask ourselves, is there some kind of analytic way of capturing parabolas like these that do not cross the horizontal axis? Because that's what we want. And at this point, perhaps the voice of your algebra teacher comes back to you to remind you that the graph of a quadratic doesn't cross the horizontal axis if the quadratic itself has no real roots, if the only roots are complex. Aha! So can I translate that condition over here into something analytic? I can if I remember the quadratic formula, which of course you do. You can probably rattle it off in your sleep. Minus b plus or minus square root of b squared minus 4ac over 2a. That thing gives you the two roots of a quadratic. The only way that it has no real roots is if that stuff under the radical, the b squared minus 4ac, if that is negative. If that's negative, then the quadratic has no real roots, and therefore its graph never crosses the horizontal axis, which means that this thing would always have the same sign. The point being that this will have the same sign for all values of h and k if and only if the discriminant of this quadratic, that b squared minus 4ac stuff that goes under the radical, namely this, is negative. And speaking of your early algebra classes, when you see something like this, you should of course have an irresistible urge to divide by 4 to clean it up, but I'm going to go one step further. I will not just divide both sides by 4, I'm going to divide both sides by negative 4. And when I do that, on the left-hand side, I will get this, and on the right-hand side, dividing by negative 4 still gives me 0, but I have to remember that when I divide both sides of an inequality by a negative, I reverse that inequality. So in this case, I will end up with greater than 0. And this expression should look very familiar. That is the expression that we called d of p in our second partial derivative test. So this last condition holds if and only if d of p is positive. Hallelujah! We have now established the link that explains the second partial derivative test. We have a critical point, p, and what we've shown is that if we take that critical point and compute this crazy thing, d of p, which is defined this way, if it happens to be positive, that means, thanks to this logical chain right here, that we have a local extremum at p. Well, that's the heart of the matter, but we still need to decide whether that local extremum is a local maximum or a local minimum. Well, that's easy. There's almost nothing else we have to do, because if that d of p is positive, that tells us, through this argument right here, that all the second directional derivatives have the same sign. So the only question for us is that sign positive or negative? Do they always look like this, or do they always look like this? Well, since it's already been guaranteed by this condition that they all have the same sign, all we have to do is check one of the second directional derivatives, find its sign, and whatever that sign is, it's going to be the sign for all of them. Well, what's the easiest specific second directional derivative to check? Well, it's going to be either one of the second pure partials. I decided to use, when I wrote down the second partials derivative test, the second partial derivative with respect to x. If that second partial with respect to x happens to be positive, under the conditions we're talking about right now, that would mean that since this is one of the infinitely many second directional derivatives, and all those second directional derivatives have the same sign, that they all have to be positive. That means we have all of them are concave up in all of those cross sections. So that means that we would definitely have a local minimum. On the other hand, if we had our critical point P and our crazy D value here is positive, but the second partial with respect to x happens to be negative, well, that second partial, once again, is one of the infinitely many second directional derivatives, and we know that they all have the same sign. So in this case, they would all be negative. So we would get concave down in every direction, which means that we would have a local maximum at P. So that secondary part of the test, once we found that this quantity is positive, that secondary part of looking at the second partial with respect to x, that's just sweeping up afterwards. And this also shows, by the way, that there was nothing special about the second partial with respect to x. We could have used the second partial with respect to y. If that's easier, you could use that. We could have used any second directional derivative right here. That's just clarifying. This tells us that all the second directional derivatives have the same sign, and this is just an easy one to compute. This is a Three Musketeers kind of situation. It's all for one and one for all. If we know what one of them is doing, we know what all of them are doing. And then the last piece of the argument would be to retrace our way through this chain if d of p happened to be negative. Well, if it's negative, then this means that this would be negative, which means that this would be positive. Everything is reversed right here because of these equivalences, which would mean that these do not all have the same sign for all h and k, which would mean this does not always have the same sign, which would mean this does not always have the same sign. And if second directional derivatives have different signs, sometimes positive, sometimes negative, well, that would give us not a local extremum, that would give us a saddle point. And that was the last piece of the second partial derivative test. That tells us why if d of p is negative, we end up with a saddle point. And now you understand why, I hope, the crazy-looking second partial derivative test actually works. It's an interesting argument. This is not the kind of argument you are likely to come up with on your own, but you should be able to appreciate its artfulness. It connects all sorts of surprising things. Who would have thought all that stuff from your first algebra courses with discriminants and graphs of quadratics would make an appearance here? Yet they do. And the cleverness of noting that dividing by something will preserve the sign of this thing and yet turn it into this weird quadratic. There's a lot of good stuff in this proof. So I hope you enjoy thinking about it. Now I want to end with a few comments about optimization in general, but I want a little room to stretch out here. And like magic, I have it. If you think about the sorts of optimization problems you have done, both in Calculus 1 and in this class, you may have wondered what the point of all the analysis was, given that I can always turn to a computer and graph a function of one real variable or a function of two real variables. And if I can do that, surely I can find these local extrema just with my own two eyes. True, I may not be able to get the exact values of the points that maximize or minimize these things, but a computer should be able to give me approximate values to whatever degree of accuracy I wish. So why go through all the trouble of computing things like this? It's a perfectly reasonable question. One answer is that, yes, sometimes we do need exact values. The second answer is that, especially with functions of two variables, it's sometimes tricky to get a decent picture, even with the help of a computer. But more importantly, what we have really done is pave the way towards optimization of scalar fields in general. Suppose, for example, that I have a function of three variables. Now there is no possibility whatsoever of looking at the graph of that thing and picking out hills and valleys. And of course, if I have a function of 4 variables, or 5 variables, or 97 variables, forget it. Graphical methods are totally useless to us. Now, I haven't shown you how to actually optimize functions of 3, 4, 5, 97 variables, or what have you. Only the case of one variable in Calculus 1 and the case of 2 variables in this class. It would be fun to go there, but we don't have the time, and this course doesn't have the prerequisites for that. You really need a little linear algebra to discuss the general problem of optimizing scalar fields from Rn to R. But at this point, I can say that we have already laid the groundwork. If we're trying to optimize such a function, the first order of business is to find critical points, to find our suspects. Well, you can imagine how we do that. We just find where the gradient of f is equal to 0. That entails solving a system of equations, generally nonlinear, which generally would involve some kind of numerical approximation. So far, nothing is different from the case of functions of two variables that we've been talking about in here. But once we have our list of critical points of such a function, then we have to have some kind of criterion for deciding whether they are local maxima or local minima, or neither. That criterion ends up looking something like this. It's more complicated, though, considerably more complicated. What happens is that your function gives rise to a particular matrix, which is called the Hessian of this function. If that matrix has certain properties, then we can conclude that we have a local extremum. And further refinements will help us decide whether it is a local maximum or a local minimum. But if you go on, as I hope you will, to take a course in which you explore such things, you will have laid the groundwork for it in your first calculus class and in this calculus class. As you have no doubt discovered already, the better you truly understand the mathematics you are learning at one level, the more it will help you to understand the mathematics you want to learn at the next level. Okay, I don't think I have anything else to say on this topic, so do svidaniya.